Okay, so in this video, we want to consider an application of differentials to measurements and uncertainty calculations. We'll look at 3 problems, and you'll see that in each problem, the idea is the same. Suppose that we have in our first problem a circle. And suppose that we have measured the radius of the circle with uncertainty. And suppose that we have r, the radius. And suppose we found a radius of, say, 2 meters plus or minus 0.03 meters. So we have now the length of the radius, 2 meters, with uncertainty, 0.03 meters. So this is the uncertainty, therefore this is the possible change in the radius, right? The answer is 2 up to a change in either direction of 0.03 meters, and change of course is d or delta. Since r here will play the role of the independent variable, delta r is equal to dr. Same thing. So suppose we find the radius of the circle, 2 meters plus or minus 0.03 meters, the uncertainty. Suppose we want to find the circumference of the circle with also uncertainty. So we'll say C is the circumference. Of the circle. Well, what we have to do is we have to relate C to R. How could you find the circumference of the circle as a function of the radius? Well, C is 2 pi r. So of course, first find the value of the circumference using the value of the radius you have obtained without uncertainty, right? So this would imply that since we took a radius, we found a radius of 2 meters, the circumference would be 2 pi times the measured value of the radius, which is 2. And we get 4 pi. And if you compute 4 pi, you'll find approximately 12.566 meters. Now what about the uncertainty? Well, the uncertainty will be the change in C, right? And that's delta C. Well, here's where we're using that the differential. We want the change in the dependent variable because C is the dependent variable that depends on R, the independent variable. And instead of finding this directly, and not directly, I mean exactly, we'll approximate this with the differential. And this makes sense because it doesn't make sense here to talk about exact uncertainty because an uncertainty is not exact by definition, right? So we'll say, and because we have a small error in the independent variable, delta r, which is the r is fairly small compared to the measurement, right? 0.03 meters is small compared to 2 meters. So delta r is fairly small. So delta c, the exact change in the circumference, the uncertainty, will be very close to the differential. Well, and now we find our differential, which will give us a pretty good estimate of the uncertainty in our circumference. Again, what is the differential? Well, the circumference is a function of r. The differential, therefore, is a derivative of c with respect to r times the change in r, dr. And again, dc over dr times dr, cancel the dr's, and you get dc. Let's compute this. dc over dr, well, this is 2 pi times r. So the derivative of c with respect to r is simply 2 pi times dr. And now we evaluate. 2 pi is a constant, that's 2 pi. dr is the change in the radius, the uncertainty in the radius, and that uncertainty is 0.03. And if you compute 2 pi times 0.03, you get approximately 0.1885 meters. And there you have it. You have found the circumference to be approximately 12.566 meters, and the uncertainty is approximately the differential, which is about 0.111885 meters. And now we have our final answer. We have found the circumference of the circle with uncertainty. So we can say the circumference is approximately 57 meters, plus or minus. On uncertainty, you could round up here, say to 0.19, so 0.19 meters. And that is our final answer. If you found the radius of the circle to be 2 meters with an uncertainty of 0.03 meters, you will then obtain a circumference of 12.57 meters with an uncertainty, which is estimated by the differential, of about 0.19 meters. And this is how you can use differentials to estimate the uncertainty in the calculation of a variable. And that's it. Let's do 2 more examples. Number 2. Suppose now that we have a cube. And we have found its volume. So imagine that you had a beaker and you submerged the cube into water, and you found the volume of the cube to be, let's say, 24 centimeters cubed, plus or minus an error of 0.2 centimeters cubed. And again here, this is your uncertainty. This is the change in volume. So this is your delta V, which is the same as dV here, because V will play the role of the independent variable. What if we ask now for from the volume, extracting the length of one of the sides of the cube? Since we have a cube, the length of each side is the same. Well, we could call this, say, x. So x is the length of a side. And now again, given that we have found a volume of 24 centimeters cubed with an uncertainty of 0.2 centimeters cubed, we would like from that to extrapolate the length of the side of our cube, of course with uncertainty. Well, if you just go back, the only thing you have to do is you have to find a way to express the new variable as a function of the original variable. If you can do this, you're good to go. Well, here, the variable that we have calculated first was the volume, that is the original variable. The variable we want to compute from this is the length. So we have to express x as a function of the volume. Well, naturally, the volume is x cubed, right? The area of the base is x times x squared times the height times x. The volume of a cube with a side of length x is x cubed, but we want x as a function of v, not v as a function of x. But it's pretty easy to solve for x as a function of v, taking the cube root on both sides. X is simply the cube root of the volume. And now we're good to go. Let's evaluate the value of x and then find the uncertainty. X is the cube root of the volume. We found a value for the volume of 24 centimeters cubed. This is 24, cube root of 24. If you compute this on your calculator, you will get approximately 2.8845 centimeters. So now we have the length of one of the sides of the cube, but we wanted the measurement of x with uncertainty. Well, the uncertainty in the x measurement is the change in x, delta x. Well, we will, instead of finding the exact change in the variable x, we will find the differential of x. which will be an approximation to the exact change in x because we have a fairly small change in the independent variable. And here be careful about this, right? We're used to seeing x as the independent variable, but here it's not the case. The independent variable is the volume, and x is now the dependent variable. X is now a function of the volume. So x depends on the value of the volume. And now we find a differential. Because x is a function of v, the differential dx is the derivative of x with respect to the independent variable. Of course, to get dx, we have to multiply by dv. Well, what is the derivative of x with respect to v? Using the power rule, we get 1/3 v to the negative 2/3 times the differential dv. Now we have our differential dx for any value of v and dv. Let's evaluate. It's 1/3 the volume to the negative 2/3, but we found a volume of 24, so that's 24. And dv is the uncertainty in our volume calculation, and that is 0.2. And if you compute this, with your calculator of course, because of the cube root of 24, you will find approximately 0.008 centimeters. And now we can give our final answer, the length of one of the sides of our cube with uncertainty. So the length, x, was approximately 2.8845, so you could say 2.884. You could round up or down here, it doesn't really matter. Let's go with 2.884 plus or minus an uncertainty of roughly 0.008 centimeters. And there you have it. So if you submerge a cube into water and you find a volume of 24 and an uncertainty of 0.2 centimeters cubed, from this we can extract that the length of one of the sides is roughly 2.884 centimeters with an uncertainty of 0.008 centimeters. Once again, simply using the differential as an approximation to the uncertainty in our variable. And as always, we needed to express the variable we were after as a function of the original variable that was calculated. Let's do one last example, and this will conclude our discussion of the differential. Let's go back to the circle now, but suppose that instead of having found the radius, we have measured the circumference of our circle. So this is our third and final problem. So we have a circle of radius, well, of a given radius. And suppose we have measured not the radius now, but we have measured with a measuring flexible tape the circumference of a circle. We'll call the circumference C. And suppose we found a circumference of 100 meters plus or minus an uncertainty of 0.6 meters. So again, C will be here our independent variable, as it is the first variable we measured. This is the uncertainty, this is the change in the circumference. This is delta C, which is the same as dc, as it's a change in the independent variable. And suppose from the circumference being 100 meters with an uncertainty of 0.6 meters, we want to find, say, the area of the circle, which we can call A. And again, not just the area, but the area with uncertainty. Well, as always, we have to express the new variable, the one that we are after measuring, with respect to the original variable that we have previously measured. Well, it's not clear how we can get the area from C, but let's look at the area as a function of r, C is a function of r, and then with a substitution, we will be able to express A as a function of C. Okay, so the circumference of a circle is 2 pi r. The area of a circle is pi r squared. So you see, A is a function of r, C is a function of r, but we want A as a function of C. Well, what if we solve for r here as a function of C? Divide across by 2 pi, and you get that r is simply the circumference over 2 pi. And now you can replace in this equality. You will get pi times the radius squared for the area, but the radius as a function of the circumference is c over 2 pi. And there you have it, the area as a function of the circumference. Let's simplify a little bit. Square this, you'll get pi over, if you square this, you'll get 4 pi squared, times the circumference squared. Well, a pi over pi squared, you can cancel one of the 2 pi's, so you're left with a pi on the bottom. So all you have is 1 over 4 pi, which is a constant multiple of c squared. And now you have the area, the variable you're trying to measure, as a function of the circumference, the variable you have previously measured with uncertainty. And now we're good to go. So our area function is 1 over 4 pi, the circumference squared. As always, let's find the value for the area, then find the uncertainty. So, the area in this case will be 1 over 4 pi. The circumference we found to be 100 meters. And if you compute this, 100 squared is 10,000 over 4 pi, you'll find approximately 795 meters squared. And that's the value for your area. Now with the uncertainty. The uncertainty is the change in the variable, so the change in A. But as always, this is the exact change in the variable A, the area of the circle. But as always, we're talking here about uncertainty. So we can estimate the change in the function, delta A, by its differential, by dA. And because now A is a function of C, the differential in A is the derivative of A with respect to C, times, well, if you want to be left with dA, you have to multiply by dC. Well, let's differentiate A with respect to C, as A is a function of C. The 1 over 4 pi stays there, it's a constant multiple, times the derivative of C squared with respect to C, that's just 2C, and times the differential dC, the change in C. We can simplify a little bit, because 2 over 4 is just 1/2, so we have C over 2 pi, times the differential dC, and now we can evaluate, right? We found C to be 100 meters, so we'll have 100 over 2 pi meters, times the differential dC, that was the change in C, the uncertainty, and the uncertainty in our measurement of C is just 0.6, sorry. So it's 100 over 2 pi times 0.6. And if you compute this, you'll find approximately an uncertainty of 9.55 meters squared. And now we can write down our final answer for the area with uncertainty. So the area is equal to, this was our value, so 795.775, so we could say 796 if you want. Or you can even keep these, doesn't really matter. Say it's 790, let's go with 795.8 plus or minus an uncertainty of 9.55 meters squared. And you see, knowing that the circle had a circumference of 100 meters with an uncertainty of 0.6 meters, we can extract from this that the area of the circle is roughly 795.8 meters squared with an uncertainty of roughly 9.55 meters squared. And that's it. Once again, all we did is we expressed the new variable as a function of the old one. We found the value of the area, and then to find the uncertainty, the change in the variable, we estimated the uncertainty with the differential, the change in the tangent line to the area, and we got an estimate on the uncertainty of roughly 9.55 meters squared. Now there's one last thing I want to mention, and this is the topic of significant figures, right? If you look at the answers I've provided, in all three cases, I didn't bother with significant figures. Let's just go back and see how would our answer change if we actually were careful with the significant figures. Let's start with this one. The answer is 795.8 with an error of approximately 10 meters squared. So there's no need to mention the 0.8 here because we're not even accurate at that point. Even this one we may not be accurate because the error could be as big as 10 meters squared. So this could also be inaccurate. So you could just say that A, if you want, you could round up to 795 or 96, and that would be a more reasonable estimate. And here you could say approximately 9.6 or even 9 or 10 meters squared. And this is slightly more reasonable because you cannot expect this digit to be accurate if the error can be as big as about 10 meters squared. Even this one, we still don't know. And you could do that and go over the other two examples and sort of fix that. But in this course, we're not so worried about the significant digits, just being able to find the uncertainty using our understanding of differentials. So don't worry too much about significant figures, just understand how to find the value of the variable and estimate the uncertainty with the help of the differential. The significant figures, as I've just said, I won't be picky about those. And that's how you apply the differential to measurements in uncertainty calculations.